Analytics. My name is Chester Chen. I'm one of the organizers for the meetup. So today we have a special guest, Gian from the Imply. Jenny is actually a frequent speaker at our meetup. I think at least gave us three times talks in the last several years about different aspects of the Apache Druid. So today's going to talk about as the title says here, the storage engine and query engine. So Jenny is the CTO or co-founder of Imply, and it's a San Francisco-based technology company, and he's PMC chair for the Apache Druid. Previously, he had worked at Modern Buckets, and which is actually the original Druid one out of it. So without further ado, Jen, take over.
Oh, let me unmute. All right, cool. Thanks for the intro. Today's talk will be about inside Apache Druid storage and query engine. Apache Druid, like Chester mentioned, something I've spoken about at SF Big Analytics before. I think the last couple of talks I gave about it were sort of how you use it, what are common use cases for this kind of system. It is a real-time analytical database sort of system. And this talk is going to be much more technical. This one is going to be under the hood. So for those of you that are interested in the internals of a database and how a system like this will work on the inside, you're in the right place. And if that is not what you're here for, then I'm sorry, but that's what you're going to get. So let's see. Let's start looking at the slides. Let's see what I got. I'm going to switch to camera 2 so I can look at where the slides are, which are over here on the screen. Can everybody? Is my screen sharing properly?
Yes.
All right, great.
Right now we see the first slide.
All right, perfect. That is exactly what you were supposed to see. Okay, so next slide. So who am I? Like we mentioned, I'm Gian Merlino. I'm a committer, and I am the current PMC chair at Apache Druid. I'm a co-founder at Imply, which is a company that is based around the Druid project. A lot of Druid committers work at Imply, not all of them, but a lot. We are hiring. So throughout this talk, if any of this stuff seems like the kind of stuff that is really interesting to you, we have open positions all across engineering. So there will be a link at the end of the talk to our careers page. But let's get into the tech. So agenda today. There's a few things I want to talk about. One is a brief introduction to Apache Druid for those of you that are not familiar, just for an orientation as to what the purpose of the software is and the space that it lives in. Then I'm going to talk about the segment concept in Druid, which is a core concept that helps understand how everything works internally. Let's talk about how data servers work. Druid is a distributed system that can be comprised of, a cluster can be comprised of tens or hundreds or even thousands of servers. We'll talk about how that works. We'll talk about how a cluster comes together from many data servers and some of the distributed system pieces that make that work. We'll talk about the segment file format. So that's a much lower level detail. And then we'll talk finally about queries and how they are executed. So we're going to actually touch on a bunch of different levels of the system and kind of give, I would say a flavor of how each level of the system works. So orientation, what is Druid? Druid is a query engine. We like to think of Druid as a rocket ship, goes really fast. But what Druid really is not a rocket ship, it's a fancy calculator. So this is a more accurate picture. Druid is a big calculator that lives in the sky, and its purpose is to add numbers up really, really quickly. Why do you want to do that? Why would you want to add numbers up really, really quickly? Well, the main reason is because you are looking to power online analytical applications also known as OLAP applications. And on the left over here, we have one example, which is the Imply application called Imply Pivot. And I like showing it with videos because I feel like its main purpose and reason for existing is to let you kind of fly through your data, interact with it, look at it from different angles. That's why we call it Pivot. And you want to be able to generate these visualizations add numbers up really quickly in different ways, different combinations of filters, different combinations of grouping, and that's what online analytics is all about. Druid doesn't just power Imply Pivot, it also speaks SQL. And so you can build your own applications on top of Druid, and many people do that. It is a very popular use case. All right. Druid in the wild, this slide is a little bit of a motivating slide. That's sort of why should you care about this system and how it works. And one reason you should care about it is that it is used at pretty big scale at some pretty major players. So Netflix uses Druid for real-time insights. Salesforce uses Druid for something very similar. Druid is enabling analytics Airbnb. And Mopub, a Twitter subsidiary, querying terabytes of data in seconds using Apache Druid. So it's a system that is really deployed at pretty massive scale at some of the companies out here in the Valley that have mountains and mountains of data. Yeah, it's also used by Imply customers. Some numbers from Imply customers. This is so at Imply we have a cloud-based service for Druid, and across this entire service, we've got petabytes of data under management, thousands of daily active users, millions of rows per second ingested, 90 percentile query time. With all that action happening is less than 1 second, 99 percentile query time less than 2 seconds. And I think this is pretty impressive. I think it's pretty great because we're not just doing point lookups. We're not doing, this isn't a key value store. This is something where every query is actually pulling large numbers of rows, aggregating across many rows at once in live on demand for each query. And so being able to do that in the sub-second, 90% of the time is pretty great, especially at the scale. And so we'll talk about, I'll be talking about how this works. Okay. So that part of the talk was sort of orientation, motivation. Hopefully it prevents you from falling asleep in the rest of the talk, but we get into the nitty-gritty details as to how we actually achieve this performance at that scale. So inside Apache Druid. Some of you may have seen this film, The Powers of 10. It's a really great film. If you haven't seen it, I would heartily recommend it. It's about 7 minutes long. It's on YouTube. You can search for it. The link is also below in the slides here. It is a film that was made a few decades ago. The concept is it sort of starts looking at this 70s kind of looking dude on a picnic blanket, hanging out in a park, and zooms away from this gentleman all the way out to the scale of the known universe, kind of discussing every zoom level along the way, and then zooms all the way in into, I think, some sort of subatomic situation in his hand, also discussing every zoom level along the way. It's a pretty neat concept, and I wanted to apply something similar to talk about Druid. So let's start at a zoom level. Let's start somewhere in the middle. It's sort of the equivalent of our picnic park dude. And then we'll zoom out and then we'll zoom in. And so we'll kind of have some commentary about each level on the way. The middle zoom level that I wanted to start at is the level of a segment. A data segment in Druid is a file. It's a single file. It's a heavily optimized storage format. Each one has about 1 million rows in it, or maybe a little bit more, but on the order of a million rows. New segments are created continuously as data is ingested. And so a cluster starts out with 0 segments, and then it eventually gets more and more and more and more. It can have hundreds of thousands or millions in the end, just depending on how much data has been loaded into the cluster. They are immutable once they're created, so they're heavily read optimized. Like I mentioned, we'll talk a little bit more later in the talk about how exactly they are structured. But for now, just think of them as immutable pieces or immutable files that have about 1 million rows of data in them. They can be dropped, replaced, or combined, which we call compaction. So that is how you would do something like a update or an overwrite or a delete in Druid. You would take these immutable segments and you would replace them with new ones. And like I said, generally 1 to 5 million rows each. So we are, with a segment, we are at this sort of 10 to the 6th row level, 1 million rows. Segments have a life cycle that I want to talk about a little bit that will, I think, make what's happening, it'll make the structure of the cluster a little bit clearer. Segments have a life cycle. So data comes into what we call an indexer. Streaming data and batch data come in. These segments are built incrementally, row by row. Once a segment has finished being built, we do what we call publishing. And when we publish that segment, we push a copy of it to what we call deep storage, which is going to be S3 or HDFS or Google storage or something like that, some kind of cloud object storage. We'll push it there, and then we will load that at some point later on a historical. A historical is another kind of process in Druid that is responsible for loading these immutable segment files and doing queries on them. And so I want to look at this life cycle a little bit more closely. So first off, the streaming data comes into the indexer. Number two, the indexer pushes that segment to deep storage. Number three, that segment is loaded from deep storage onto a historical. And then number four, it's on the historical, it's available for querying. At that point, you can query it. You may have many historicals, and new segments are constantly coming in. They're constantly being dropped and replaced, and there's sort of this continuous flow of segments to the system. The affinity of segment to server is pretty loose, and so segments can move around from server to server in a process that we call balancing. And so balancing means that what's going to happen is another historical, a different one, will load the same segment, and then the original one will drop it. So for a brief period of time, it'll be available on both, and then it'll drop from the first one. And this balancing process is happening continuously in the background to try to keep the load even across all the servers. The fact that this is one of the reasons why we do have this segment concept. The idea is that by packaging your table into these little chunks, each one being one file that has about 1 million rows in it, we can, this process of having data backed up on deep storage, this process of balancing data between servers becomes relatively straightforward for us to do. It's just a matter of moving these files around. Okay, so now I want to zoom out one level and look at what's happening in a data server. So we're not looking at one segment anymore. We're now looking at a whole data server. A data server is going to have, it could have thousands of segments on it. It could have tens of thousands of segments. There's generally going to be many more segments than data servers because they are kind of flying around in this balancing way. And so a data server is at about a 10 to the 10 row size, so about 10 billion rows per data server. We have a few goals for the data servers that inform the design. And so, like I mentioned, I want to give a flavor of how each of these pieces of the system is designed. And so the goals for the data server design, number one is a CPU-oriented goal. We want to be able to harness all the available CPUs for a single query. That means that if there's only a single query running on the system, we want every single CPU in the entire cluster to be able to participate in that one query. And that's a goal of maximum parallelism. We have another goal that kind of works against that goal. They're at odds with each other, which is we also want to balance CPU use optimally across concurrent queries. So if we have many queries running, then we want them to share CPUs. We don't want a single one to hog everything. And I'll talk a little bit about how that's achieved on the next slide. But till then, we also have goals for memory. So we want to be able to take advantage of high memory hardware, which means that basically we don't want to box ourselves into a design where we always are needing to read data over the network or over the disk or something like that. If you have enough memory for your data set to be memory, we want it to be in memory. If you don't, that's fine. Like we can load it from disk or wherever it is. But if you have the memory, we want to use it. We want to fall back to disk when memory is insufficient. And when we're thinking about these goals, we generally kind of think of data sets in two categories. We sort of think of these hot data sets that are generally going to be about half to 80% of the data set will be in memory, and then a cold data set where less than 10% will be in memory. and we want to make sure that we want to try to have a reasonable performance profile and reasonable hardware usage profile for each kind of data set. Okay, so that being said, those are the goals. How do we achieve those goals? So this picture here is sort of a schematic picture of a data server. And I want to call attention to some of these pieces and talk about how they help us achieve the goals. So first off, this memory map disk. Druid, like all programmers, the programmers that write Druid are lazy. And like all good lazy programmers, which is a virtue, I think. I think it's better if programmers are lazy. The ones that aren't lazy are writing a bunch of code that is not really necessary. So like all good lazy programmers, we will let something else handle something if it makes sense. And so we let the OS handle the memory, the disk memory caching. So what we do is we use a technique that's used by a lot of data systems, memory mapping. We have files on disk that are memory mapped, and that just means that the OS, which is usually Linux, could be whatever, I guess, but it's usually Linux. So the OS is going to has a page cache, and the page cache is going to cache chunks of those files in memory, potentially the entire file if you have enough memory. If you don't have enough file, the cache will be it'll cache as much as it can and read the rest from disk from whatever is not in the cache. And so this helps us achieve our goal of using the memory if we have it, and if we don't have it, falling back to disk, using that sort of leveraging this memory mapping concept. In order to make this work, we have to write our code and design our data structures in such a way that we don't have to have that the on disk format is the same as the in-memory format. So we can't have a system where the on-disk format needs to be decoded to be read in memory. So the on-disk format can't be something like JSON or TSV, because those need to be translated into in-memory structures to make sense. And so we have to have the in-memory structures and the file format be the same. But that's a small price to pay because memory mapping is awesome. Moving up a layer, we have a pool of processors and a pool of memory. So the processing thread pool, there's one per CPU, one thread per CPU. And this is how we enable our goal of using of maximum parallelism. What we do is one processor or each of these segments is processed in a sort of single threaded way. But if a query is going to hit 1,000 segments on a server and the server has 30 processors, then we can take those 1,000 segments, divide them up 30 ways, and then each processor can get its share of segments. They can all process in parallel. They can get through the 1,000, and much more quickly. And so that's the main reason, or that's a main reason why we always want to have many more segments than servers. This enables this parallelism. And the other thing we need to do is make sure that a query can't starve other queries. And so what we do there is we have one concept of query prioritization. And so what we do is every time a single segment is finished being scanned, we check to see if there's another query at higher priority. And if there is, then we preempt the earlier query. The higher priority query gets to process its segments, and then we come back to the lower priority one later. And so the processing of individual segments on a per query basis is constantly being interleaved based on query priority. The memory pool and the per query resources at the top, the per query resources at the top are things like HTTP connections, HTTP server threads, stuff like that, things where there's one per query. Those are divided up on a per query basis. Every query gets a fixed amount. And we also need to prevent starvation there. And so the way we prevent starvation there is we limit the concurrency that low priority queries can have. So we always save a little bit of these resources, these per query resources for high priority queries. The nice thing about that is that a low priority query, we're sort of limiting the concurrency of low priority queries. So we won't let, let's say the max concurrency is 100. Maybe we'll run up to 80 low priority queries at a time to make sure there's always room for 20 high priority ones. The low priority ones can still use every processor because the processors are interleaved at a finer grain level. So the fact that we have these multiple stages here, multiple layers, enables better interleaving than if we only had one layer. And that's why we do it that way. Okay, let's see. One more zoom level up, how a cluster comes together. So we have these data servers, and these data servers all have, their 1,000 or 10,000 segments. They have their few dozen processors. They have however many, maybe they can run 100 queries concurrently each, and so they have their 100 queries. They're interleaving which segments are getting processed by which processors. They're having a great time. And then how do they become a cluster? Now we're up one more zoom level. You can have about up to 1,000 servers in a cluster before you start hitting metadata, scaling bottlenecks and stuff like that. So we usually recommend maxing out around 1,000 or 2,000 servers per cluster. Most people don't hit it. Some do, which is, I think, really cool. I mean, it's cool to have 1,000 servers in a cluster. And for the people that are, I guess, lucky enough to have clusters that big, we usually recommend that once you hit 1,000 or 2,000, then you consider splitting into multiple clusters. But most people are going to have one cluster that's going to have tens or hundreds of servers. And the way that they are stitched together is with the process we call query fan out. Query fan out, we have is visualized here. At the top, you see the query server with a broker in it. When you, the user, makes a query to the system, you query the broker. The broker knows what segments are on what data servers, and then it will fan out to those segments. And there's some smart things it does here. It will use the filters for your query to prune the list of segments to fan out. So if you have 100,000 segments in your cluster, but then you have a time filter on your query, or you have a filter on a column that you're partitioned by, then the broker is smart enough to understand that certain segments might not have any data for a certain time range, or might not have any data for a certain partition, and it will not include them in the fan out. Of course, if you don't have any filters like that, if you're not, if you're filtering by something that you're not partitioning by, then the broker will involve every segment in the query, which is fine. It's fine because we can process them quickly, which is the next thing we'll talk about. So the next thing we'll talk about, we're back at the picnic. We're back at the picnic blanket in the park, and we're going to start zooming into the segment and see what happens inside. So let's say that we do have a query that has to hit every segment. We need to blast through them all as quickly as possible. How do we do that without falling apart? So back to segments. Let's talk about that. I think to understand that, we need to talk about the segment format. And so this is part of why we're zooming in. Here is a segment with a data set that is concert ticket sales in various cities for various artists. This is a segment that has 8 rows in it. You can tell it has 8 rows because there's 8 values in the data section of every column. So the first here, we have the time column. The time column is just a timestamp. It's the time that these tickets were sold. The timestamp column is pretty special in Druid. We have a lot of special handling for it. It handles things like you can set time-based retention policies. You can do time-based data overwriting, time-based filter pruning. So there's a lot of special stuff with regard to the timestamp. It's actually a mandatory column. So every table has a timestamp column. Even if you don't have one, you can set them all to 0 or whatever, but it's still going to be there. Here's the artist column. And so this is the artist that the tickets were sold for in this example. In the data section, there are 8 values because there's 8 rows in the segment. And so this is saying the first 3 rows are 0, and then the next 2 are 1, and the next 3 are 2. There's a dictionary. So the way we store strings is we dictionary code them. And the dictionary codes are, you can think of it like assigning an ID to something, like if you had a star schema in a dimension table. You can also think of it sort of like a pointer, because the dictionary is actually an array, and the dictionary code in the data section is almost like a index into that array. So you can think of it kind of either way. I think both ways of thinking about it are valid. In this situation, there's 3 artists: Justin, Kesha, Miley, 0, 1, and 2. So the first 3 rows here are Justin, and so on and so forth. And then finally, we have an index, and the index is per column. It's stored compressed. It's a bitmap index. We use an algorithm called roaring to store that compressed. It's a pretty cool algorithm. This is, I guess, technically not necessary to serve queries, but it speeds them up. So that's what we call an index. It's positionally correspondent to the dictionary. So the first index here corresponds to the first dictionary entry. So Justin is the first one. 0, 1, 2 is saying that Justin appears in rows, the first 3 rows, which that value does appear in the first 3 rows. So that's good. The slide's correct. I'll skip city. It's kind of the same as artist. And then finally, we have here price and count. These are integer columns, long columns, so 64-bit ints. And they're basically the same as the time column. They're going to be stored. Just one note here, this stuff is, of course, not stored literally like this. We don't actually, the way we store each of the data sections for each of these segments is something that's specific to that data format. So for a long column, what we're going to do is we're going to analyze the value distribution in the long column. If they're like totally completely random and they use all the way up to 64 bits, then we'll just store them as is. But a lot of real world data is not like that. A lot of real world data is not just totally random. It's common in a real world situation for everything to be in a small range. And so if that's the case, we'll use delta encoding, or we'll use table encoding, or a variable bit length encoding, something like that, in order to not have to use a full 64 bits for every value and compress them further. Let's see. Okay. So I want to go through a query and talk about how we're going to execute this query on this segment. And I think this is going to be something that illustrates sort of how a system like this can blaze through so much data so quickly. So here's a query that selects city and sum of price, where artist equals Justin, group by city. So what we're going to do is we're going to get the total amount of money spent on tickets broken down by city for a particular artist. Relatively simple query. The first thing we're going to do is we are going to resolve the filter, artist equals Justin. We have to figure out what rows match the filter first. And we're going to do that by looking at the dictionary. The dictionaries are all alphabetically sorted, so we can binary search through them. We don't have to do a linear scan. In this situation, it doesn't help that much because only 3 entries. But there could be thousands of entries in a dictionary, or tens of thousands, and it helps more and more the more entries there are. So we're going to do a binary search. We're going to realize that Justin is 0. Then we are going to go over to the index, and we're going to remember that the index and dictionary are positionally equivalent. So we're going to go to the index. We're going to read the first bitmap out, 0, 1, 2. We are going to see that those first 3 rows are the ones that match our filter. At that point, we're done with the artist column. We don't need to read the data section because we got all the info we needed from the dictionary and the index. Then we're going to go to the city and price columns and walk them simultaneously to do the group by, because we're grouping by city and then adding the price. We only look at the first 3 rows because we know from the index of the artist that the first 3 rows are what matches our filter. And so we build a little table, a little temporary table you see up here in the top of the screen. 0 is null, 1 is 2912, 2 is 3753. And that's the result of the group by. One thing that's, I think, important to notice is that at this point, the dictionary codes there are used as the keys, 0, 1, and 2. So we're having actually integer keys, not string keys. And this is one of the big reasons that we do dictionary coding. It's not just a compression technique. It also enables us to operate on these dictionary IDs while we're doing group bys, which is super, super useful because we're a computer, and computers are a lot faster when they're running on integers than when they're running on strings. So this speeds things up a lot. Then at the end of the group by, then we replace the dictionary codes with the actual strings. And the idea here is that probably there's probably gonna be fewer result rows in the group by than there were input rows, because things are actually getting grouped a little bit. And so we're gonna read we're gonna read the string operations. The string operations will scale with the size of the result set of the group by, not with the input set, which is good. Anyway, then we're done. Then we tossed the null out, and now we have the result for the segment. And you can see that we were very economical with what we read out of the segment. We did a binary search through one dictionary. We did a random access in an index. We just read one block out of 2 columns. And then we did 2 random accesses out of the dictionary for one of those columns. And it's a pretty minimal amount of work. It's deferring expensive things like string operations until as late as possible. And it's techniques like this, minimizing the amount of data we read, minimizing scans, doing searches when possible, deferring dictionary lookups. These techniques enable rapid processing of data. The final thing I want to talk about is one more zoom level down, which I think I just have a little bit of an aside here that I think is really cool about behavior that happens within blocks within segments. So let me say what I mean by that. Every segment I said is a file that has about 1 million rows in it, but they're made of blocks, and each block has about 1,000 rows in it. And so at the level of 1,000 rows, about 10 to the 3 rows. Let's look at what we have. So here, we have this 8-row column. This is the artist column from the previous example. I blew it out here to 16 rows. So it's not the same data, so don't expect it to match. That maybe this picture is a little bit confusing now that I look at it. But it's a different data set, but it's sort of similar. It's got 16 rows instead of 8. And here there's 4 blocks. I've made it so the data set is grouped into blocks of 4 blocks of 4. One interesting thing to look at is, let's say that we are trying to read data for, let's say, Miley. So Miley is 2, and the 2s appear in 3 out of the 4 blocks. So what that means is that we have to read 3 out of the 4 blocks if we're filtering on artist equals Miley. And if we're often filtering by artist, this can be pretty wasteful. It can be wasteful to have the data all jumbled up like this. It can be because the big reason for that is that each of these blocks is individually compressed. And so if we're not reading anything from a block, we can skip it. And if we are reading even the single row from a block, we can't skip it. We have to decompress the block and then decode the value that we're reading. And in practice, these blocks can have 1,000 rows in them, and decompressing 1,000 rows just to read one is pretty wasteful. So this opens up an idea here. So in a lot of data systems, you're allowed to partition by stuff. You're allowed to cluster by stuff. And there's sort of 2 reasons why that's good in most data systems, and Druid's included. One reason is pruning the list of files you need to read. So, I mentioned that if you have a time filter or you're filtering on your partition column, then we can prune the list of segments of the ones that match that filter. But there's another reason it's useful to even cluster things within a segment, which is this block skipping stuff. A lot of data systems do support the ability to skip whole blocks of data. This block-oriented design is somewhat common in columnar architectures. And so if we sort here, if we cluster by artist, now it looks like this picture on the right, where all the zeros are together, all the 1s are together, and all the 2s are together. Of course, we can only cluster by one column at a time. We can't cluster by every column. That wouldn't make sense, because we're sort of sorting the entire segment by whatever we're clustering by. But if we're often filtering by artist, you'd want to cluster by artist. And now what this means is that we're only reading 2 blocks to get Miley instead of 3 blocks. And so we've made things more efficient. A real world example, I'll leave with this, is here's a real world example from a real customer, a real Druid user that had some unclustered data. And what you can see is, look at all this stuff. Look at every single stack trace here. This is a profile. At this profile, net.jpoons.lz4, lz4 decompress safe. This is the routine that decompresses a block through lz4 compressed in Druid's case. There's so much of this happening because the data is so jumbled up that we're filtering down to, in this case, about 1% of the data set for every query. And most of the time is being spent decompressing blocks just to read a few rows out of those blocks. This profile here is after we clustered it by the column we were typically filtering by, that again got us down to about 1% of that data set. And now you see that the amount of time being spent decompressing blocks instead of 90% of the time is like 20% of the time. And the overall CPU time is 8 times lower. So the queries are running 8 times faster. And it's the same number of rows. It's the same queries. It's the same partitioning mechanism. So we didn't change any of that stuff. All we changed was the way that rows are ordered within a segment. And it made this huge difference. And so I think the reason I like this particular anecdote is because I think it shows that really every level of the system is important. All the way from, well, we're not talking about a single row, but all the way from a block within a segment that has 1,000 rows up until the trillions and trillions of row level of a giant cluster and everything in between. I guess we can talk about one row though, because I made a slide about it. So one single row, the final zoom level, 10 to the 0 rows, one row. Each row has type specific compression, like I mentioned, for strings, dictionary encoding, for integers, delta, table encoding, and bit packing. For indexes, rowing bitmap, like I mentioned. The way that things are laid out is that each value of a row, each field is spread out across all the relevant columns. So that's what we mean when we say a columnar architecture. If we're only reading 2 fields out of a row, we only have to unpack data from those 2 columns. Each one can be loaded into memory separately. And we want to cluster rows together that are likely to be queried together. Like I was saying earlier in the last couple slides, this concept of blocks is important to think about. Okay, so that was what I wanted to say. Hopefully, this was an interesting talk for those of you that are interested in how databases work on the inside. It gives you a flavor of how Apache Druid works, a real-time analytical database for OLAP apps. A lot of the techniques that we use are used by a lot of other data systems. So if you use stuff like Parquet or Orc or Presto or anything like that, those systems are using a lot of these similar techniques. And so it does help to, I think, understand how they work and think about them as you think about how to, even if you're not working on these systems, just using them in ways that are the most effective. If you want to hear more Druid content, follow us on Twitter, Druid.io. You can join the community. We're an Apache project, so we're very welcoming and open. Druid.apache.org, and like I mentioned and promised it earlier, we are hiring for Druid and Imply. If you're interested in working on this stuff full time, go on over to imply.io/careers. Thank you. Thank you for coming.
And this is a great talks. Thank you, Gian. We're open to questions. The question can post to the Slack channel. Bill, some people complain that they cannot post a question to everybody. If you can check on that. We got a first question from Louisa. He says indexer is the same as a middles manager.
I can tell that you are have used Druid before. Yes, so the indexer is like a newer middle manager. It's actually still experimental. But I like the word. I think makes more sense to people that are new to the system, because middle manager is like, what does that even mean? And indexer, I think, makes sense. It loads data and indexes it. But logically, they're the same. They're interchangeable for each other. You can use an indexer in place of a middle manager or vice versa. The only difference is that the middle manager runs tasks in separate processes, and the indexer runs every task all in the same single process.
Okay, I got a question for you on your relative to the, I think the second slide. You talk about the single row. when you have the strings and you're basically dictionary coded, then it said it's integer, you're using delta table format and some other things. So can you explain a little bit more on that?
Yeah. So I did gloss over it a bit just because, I guess time, but getting into a little bit more detail on that. So integers are really important in any analytical system because we're dictionary coding strings, and so strings become integers. Of course, a lot of data is natively an integer, and so it's an important kind of data type. And the way that we code them is like I said, when we're building a segment, we look through everything in a column. We analyze the distribution of the data that we see, and we basically decide what we're going to do based on distribution. And the logic is something like this: if there's a small number of values, so if the number of unique integers is relatively modest, and they're kind of all spread out, then we will we'll use what we call table encoding, which is we'll basically renumber them. So, let's say that in a simple example, let's say there's only 5 that ever appear, 0, 100, 1 million, 10 million, and 1 billion. And those are the only ones that anyone ever sees. So what we'll do is we'll renumber those to, 0, 1, 2, 3, 4, or whatever, but we'll renumber them to small numbers, and then we'll bitpack them. And so, numbers 0 through 4 can be bitpacked into 2 bits, I guess, maybe 3 bits. They can be bitpacked into 3 bits. And so we'll store 3 bits per row. If that's not the case, if there's a lot of them, but they're all in a tight range, this is really common for time fields. So it's typical for timestamps are really big, like the numbers are big, but they're all very close to each other for the same hour or the same day. So for something like time, what we'll do is we'll detect that they're all very close to each other, and we will do a offset. And so we'll say, we call that like an offset based encoding. And so we'll take the min time that we see and shift everything so that is 0 and everything else is shifted down accordingly by subtracting that. And then we'll pack that into a number of bits that's minimal. And then at query time, we'll unpack those bits and then add the base value. If neither of those approaches matches, then what we'll do is we will look at the min and max value that we see, and we'll bitpack that based on the min and max value. So if the highest value we see can fit into 40 bits, then we'll use 40 bits per row. And so this is, we kind of have a bunch of techniques we can use that try to pack things as small as possible. And the fallback, if none of them apply, is we'll store a full 64 bits per row, which really doesn't happen that often. It's mostly going to happen if your data is like random or something.
Okay, got it. Thank you for all the details.
Yeah. And one other comment for that, I just want to say something that a commentary about how I think it's really, understanding how these systems work can really affect how you use them and how you think about them. And it can also affect how you benchmark them. And so one thing that I see people do sometimes when they benchmark is generate random data. And you don't want to do that. You don't want to generate random data because what I just described is these systems like Druid will store data differently if it's random and if it has some structure. Like we can exploit structure if it exists. And so if you're doing benchmarking, you always want to try to generate data that has some similar structure to your real data because a system might be able to take advantage of it.
Got it. That makes sense. Another question is from the audience. It says, so what if string columns have high cardinality? Would not be highly increase the size of the dictionary?
Yeah, that is, it will. And so if the string column has very high cardinality, like let's say in the extreme example where the cardinality of the column is equal to the number of rows, so like every value is unique. In that case, the dictionary coding just kind of degenerates to being like basically the same as storing the strings as is. You could think of it as, at that point, you could really think of the dictionary codes as pointers because each one's going to be unique and is going to correspond to a location in memory that has the full string. And so behaviorally and performance-wise, it's mostly equivalent to just storing every string separately. So I guess it's no worse than that, but no better either.
Cool. Any other questions? Let's see, and just make sure. Yeah, any other questions you can post? Or Bill, I can unmute people so they can talk directly, right? Or you can do that, Bill. So there is another question. Is there a plan to implement a multi-thread broker query?
Oh, yes, there actually, that has been implemented recently. I don't remember what version it's in, but one of the recent ones added a parallel broker merge feature that I think is probably what you're talking about. So I mentioned that fan out, that where the broker fans things out to data servers. Up until I think a couple of releases ago, the result merge that happens when the results get fanned in was single threaded per query. So we could parallelize across queries, but not a single query. A single query we get merged single threaded. And that is no longer the case. A single query can get merged multi-threaded now. That was a cool feature. It speeds up. I guess it has an especially big effect on situations where you have like a group by where the result set is fairly large, like millions of rows in the result set.
So I got another question. Since the audience didn't ask question, I don't ask another question. So
Sure.
as you know, I tried to set up the Druid. This is a couple of years ago, of course, with your team's help. But that time, I noticed that Druid has a lot of services, so five, I think it's 5 services. So to get the thing set up initially is actually quite challenging. So is there any improvements in that direction to make it easier for people who want to set up Druid and make it easier to set up initially quickly?
Yeah, that's a good question. There's a bunch of stuff happening. Some of it's in the open source community and as part of Apache Druid, and some of it's on the Imply side. And I'll talk a little bit about both. Obviously, Imply is pretty invested in making Druid easier to deploy. So like some stuff happened. Yeah, anyway, some stuff's on one side, some stuff's on the other side. So on the Apache Druid side, the indexer I was talking about that is like that sort of brings all these tasks, these ingestion tasks to run in a single process is a big part of that. The idea being that it is going to be simpler for users to reason about and to configure a situation where there's just one process rather than a process that launches other processes, and you have to think about 2 levels of processes. So it makes things simpler from a DevOps perspective. Another one is we did some combinations of services. So the coordinator and overlord are one of them. These are 2 things that run in the master server. One is responsible for historical data and one's responsible for new data. They're both sorts of coordination services. They can run in one process now, and they do run in one process by default. So there's been some consolidation on the open source side, just to reduce the number. We don't really want to reduce it. Our attitude is we don't want to reduce it all the way to 1, because we kind of like that these things can be scaled independently, especially the indexing and historical and broker, because these are all doing very different kinds of work, and it's nice to be able to scale them independently and even use different machine types and even have auto scaling for one but not the other, that kind of thing. You might imagine having auto scaling for ingestion, but not for query, or vice versa. But we're giving people the tools on the open source side to, when they're not taking advantage of independent scaling, to consolidate things a bit. And then on the Imply side, it's the effort is mostly in managed services. So we have a Kubernetes based manager, and we have a Imply Cloud manager that runs in AWS and just kind of does everything for you, one click. And so it's on the Imply side, it's we're doing pretty standard open source vendor one click stuff.
I see. On the Imply side, is can data stay within the company, or the data have to shift to a different account?
Good question. There's actually 2 products there. There's one where the data stays completely on your side, and one where the data shifts to our side. The one where it shifts to our side is, of course, easier to manage, but the data has to move, and so not everybody likes that. And the one where the data stays on the customer side is, I think, it's still much easier to manage than an open source, but it's tougher to manage than when the data goes to our side. So it's kind of trade-offs between ease of management and kind of control over the environment. And I think those trade-offs are, from what I've seen in other open source companies, like you kind of get the same thing with a lot of these open source managed offerings.
True. I get another question. Let's see, maybe it's a comment. So we plan to deploy Druid on AWS and do a POC on it. Are there do's and don'ts you can think of? What the best practice? What's the best advice for if somebody want to do a POC on Druid?
Yeah, well, with my Imply hat on, I think the best advice is to contact us. We're experts in this sort of thing, and we're happy to help. We also, like I mentioned, have an AWS like native service that's one click and pretty nice. And then with my Imply hat off for a bit, I would say if you are going the DIY open source way, there's I think the most important document on the Apache Druid site is this search for the basic cluster tuning documentation. It talks about sort of how to think about for a server of a given size, what the right value is for, how much heap size to use in the JVM and how many threads to use for various things. And the most important part to get right at first is just making sure that those things are values that make sense for the size of instance you're using, which at least for the data servers is probably going to be some kind of i3 or maybe M5D, or those are the two most common ones. So I would say that's also a best practice, is to look at i3 or M5D on the data server side.
Yeah, I remember when I first tried it a couple of years ago, I think the one difficulty for me was try to find if I did something wrong, something didn't work, where should I start? And the logging, the corresponding to the changes on the, what we call index files or whatever the spec. If you change the spec, and of course here, since I don't know, I changed something wrong and then things didn't work as I expected, and then say, okay, what I supposed to do? And then I read the document, it seems like I did it right. And then, so that I think of the logging part sometimes. And
yeah, well, we certainly put a lot of work into that over the last couple of years. And I think I'm pretty happy with what the team's been able to improve there. So I think you're definitely an early adopter. So I love you for that. You're the kind of guy that loves to early adopt things and host meetups like this. And I think people that are jumping in now are going to have hopefully a better experience.
Yeah, probably when I get a chance to try it again. Okay, any other questions? Jenny is a frequent speaker, but he got a really insight all these Druid engine and the core engines. He has done this for many years, so highly respect his knowledge, expertise on these things. So if this is your chance, so give him another second to see anybody has other questions. So if not, and we'll like to thanks Jen and thanks come to San Francisco Big Analytics again, for the great talk for the audience. And I also want to thank Bill from AI Camp to help us to set up with the Zooms. And so, I always appreciated the partnerships. So, of course, you can reach out to Jen separately, our comments. So all the recordings will be posted. And Jen, it's okay. We publish this on YouTube, right?
Yeah, go for it.
Okay. Yes. So
you got me on video saying that.
So yeah, we'll post the YouTube once the recording is on the YouTube, and then we'll post it on the meetup page, so you can get from there. Okay. Thank you everybody to attending. Thank you, Jen, for speaking. See you next time.
Thanks for the invitation. It's always a